Hi all, welcome back. In today's video, we want to cover the topic of tangent planes. Now, in single variable calculus, we have the notion of a tangent line, such that if I have a graph and it's differentiable, and I want to know what the instantaneous rate of change is here, the instantaneous slope is here, I can find that with the derivative. So thus, I can find a tangent line for that point on the graph. That's a very helpful tool that we have in single variable calculus. However, in multivariable calculus, it's hard to define a tangent line because, well, how do we define a tangent line? Because if we have a point, the line can be skewed in any direction around a tangency. So what we do instead is we define a tangent plane. So now you can really see why we spent so much time talking about 3D space and how we can define planes. That's because now, instead of using tangent lines, we're going to be using tangent planes. And of course, that's something very important. So that's in the two-dimensional case. In the three-dimensional, four-dimensional case, we don't really have an analog for a plane or a line at that point. So we just call it a tangent object to our function. But we'll talk about that later. As you can see, the formula we have is very expandable, and you'll be able to see why that is. All right, let's get started. So let's begin with the derivation. So the derivation will start with the equation for a plane, which we determined back in single variable, or back in the first unit, that the equation for a plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Now we can rearrange this and make a substitution, letting little a equal negative big A over big C, and little b equal negative big B over big C. Thus we can define z minus z naught equals a times x minus x naught plus b times y minus y naught. Okay, so what does this actually look like? This will actually look like a first-order Taylor polynomial for a multivariable function of two variables. So in multivariable calculus, we don't explicitly talk about sequences in series just because the computation complexity gets a lot higher. But essentially, in the first-order case of a Taylor series for multivariable functions, what you have is your first term is just the sum of all of these for each of your variables. So if we had 4 variables, then it would be plus c times z minus z naught plus d times w minus w naught. You get the picture. But essentially, now we just need to determine what these terms are, and in a first order Taylor series in single variable, that is usually f prime at a over 1 factorial. So that's just f prime of a. So actually, what these are going to be, a and b, are going to be our partial derivatives. So we get that z minus z naught is equal to partial x at x naught comma y naught times x minus x naught plus partial y of x minus x naught comma y naught times y minus y naught. So this looks very similar to the equation for a line and point slope form, but it is also a first-order Taylor polynomial for our function, which is, of course, the linear approximation. And, of course, with all the second derivative terms that we discussed a couple videos back, you can obviously generalize that to multiple terms, but as you can see with how the higher-order derivatives work in multiple variables, it gets quite tedious. So we have our equation for how to find the tangent plane. Now we just need to apply it. So let's try an example. Let's find the tangent plane at the point 1, 1, 3 for the function f of xy equals 2x squared plus y squared. So what we want to do first is we want to find our partial derivatives at our points. So x naught comma y naught is equal to 1 comma 1, because that is our x and y coordinates of our point, right? So what we do is we take our partial derivative with respect to x, which is 4x, we just differentiate this term, and then if we evaluate partial x at 1 comma 1, then that's equal to 4, because we plug in 1 for x and y doesn't really matter, so we get 4. Then, if I take my partial derivative of f with respect to y, I get 2y. If I take the partial derivative at 1, 1, then I will get 2, because I just plug in 2 for the y there. So now we just need to plug it into our formula, and what we get is z minus z naught is 3, z minus 3 equals 4 times x minus 1 plus 2 times y minus 1. And now we can simplify, push the 3 to the other side, and we get z equals 4 times x minus 1 plus 2 times y minus 1 plus 3. And we can see what this looks like. Here we have our point up around here, and we've got our tangent plane all over in this area. And then we've got our elliptic paraboloid here, which is, of course, the function we were trying to determine. So in the next video, we're going to make a generalization here. Usually after you cover these tangent lines and tangent planes in single variable calculus, you move on to linear approximations. So we're going to move over to linear approximations. Then after that, we will discuss differentials before moving on to the multivariable chain rule. Thanks for watching, and we'll see you in the next video. Bye.